And then we're going to close out with some basic probability rules. The first that I have here is written for you, the multiplication rule. You might have seen this before. This is just an FYI. We're not going to test you over this, but it says if the probability of two events, um, if we're interested in the probability that two events both happen, A and B, we can find that by multiplying the probability of A times the probability of B given A. This is just kind of to show you that these ideas of conditional probability can be used in probability questions. What's the probability of you making it to class on time and you choosing to eat lunch at Burger King? Right? We can find that out by saying what's the probability of A times the probability of B given A. If A and B are independent, as we talked about before, this B given A can just become B, right? Because the given part doesn't matter if the two events are independent. The second one is one we will use. It's the addition rule. So the key here, multiplication, if you see and, we multiply the addition rule, or we add, right? The probability of either one of two events happening, A or B, is equal to the probability of A plus the probability of B minus the probability of A and B. And you might look at it and say, whoa, what just happened? All right, what we're saying is the first rule that I have there, again, just for your background knowledge, is if I'm interested in the question, what is the probability that this and this both happen? The addition rule helps us if I'm interested in the question, what is the probability of this or this happening? So any question is, what's the probability of this or this happening? We turn to the addition rule. Or means add in probability land. And so we add the two probabilities and you say, but why are we subtracting? Well, think about it like this. The probability of A and B is that overlap. It's that intersection where both A and B happen. And if I think about a Venn diagram, if you were to shade a Venn diagram and there's an overlap part in that, and I say, what's the probability of A? And I add the probability of B, I would double shade that little intersection. And so I have to subtract that back out. Okay, because the probability of A includes A and B, because A and B is when they both happen. So by definition, just the probability of A includes all the times where A happens and B doesn't, and has the times where A happens and B does, right? So this is included as a subset within this. It's also included as a subset within this, because this is the probability that B happens. Well, that's made up of all the times that B happens and A doesn't, along with all the times that B happens and A does. And so now I've counted the times that B happens with A and the times that A happens with B. Those are the same thing twice. Got to get rid of them once. The benefit for us is that when we have events A and B that are mutually exclusive, remember we talked about that earlier on the page, two events that cannot happen at the same time. If they can't happen at the same time, we said that the probability of A and B is equal to 0. If you look up just a few lines, you'll see that. So if events A and B are mutually exclusive, we don't have to worry about subtracting that piece off. And for us in statistics, that's what's mostly going to happen, because we're almost always going to be dealing with events A and B that are mutually exclusive. So for us, anytime we have an I need to know the probability of this or this happening, I'll just be able to add the two probabilities. It's going to make your life really nice. I'm going through this and spending a couple of minutes here because I want to make sure you understand that's a nicety to statistics, and that doesn't always happen, okay? I can't just teach you something that's wrong because it only applies here. It'd be like, when you were a kid, if your teacher said, hey, guess what? Multiplication and addition are the same thing because 2 times 2 equals 4 and 2 plus 2 equals 4. Well, you'd say that's only one case, right? In other cases, multiplication and addition give you different answers, right? That's just a one case kind of thing. And that's what happens here, is that in these cases, we get to ignore that part, but that's the rule says we have to subtract out the intersection. But again, just we get to live in a nice land where we don't have to stress about that. Okay, so we're going to confirm that we have mutually exclusive events. We're almost always going to have them. We're just, hey, these two things can't happen at the same time. And it'll be things that make sense. It won't be overly complicated. I'm not going to have you think too hard about it. You just have to do a quick sanity check. It'll be something like x greater than 5 and x less than 3. And you'd say, oh, x can't both be greater than 5 and less than 3. It's one or the other, right? It can't be both. It can be neither, but it can't be both. And so when you say, well, it can't be both, that means mutually exclusive. That means this part doesn't matter, which means in that case, I can just add the two probabilities and move on with life. Okay. So a quick example, let you pause here if you want to work through these problems. I'll give a quick pause in between each one as well. First one, find the probability of A. If events A, B, and C are all equally likely, that means they all have the same chance of happening. So again, to find a probability, we just say how many ways can something happen divided by how many total options are there. In that case, this would be 1 out of 3. Next one, find the probability of a prime. And this is the complement idea. We know that the complement is everything else, and we know its probability is 1 minus the probability of the initial event. So the probability of a prime is equal to 1 minus the probability of A. And this is going to be something that we do a lot in this course. Should be very comfortable with this idea of saying, if I want to know the probability of the complement of something, I just do 1 minus the probability of that something. In this case, probability of A complement is 1 minus probability of A, so that would just be 1 minus 1/3, which is 2/3. You can verify this just by thinking through the concept. If events A, B, and C are all equally likely, there's 3 of them. Mutually exclusive, they can't happen at the same time, there's no weird overlap thing happening, then A complement is made up of B and C. What's the probability that B and C happen? Well, there's 2 of them. They're all equally likely, so 2 out of 3, right? And then the last one, find the probability of A or B. And again, because they're mutually exclusive, we don't have to deal with this and nonsense. We can just say that's the probability of A plus the probability of B. Each one is 1/3. And so you'd get 2/3. And again, logically, you could sit here and answer this question logically. What's the probability of A or B happening? Well, how many ways, again, probability, how many ways can something happen over how many things are there, right? There's 2 ways that could happen, A or B. There's 3 things total that can happen, A or B or C, 2 out of 3, right? I want you to be able to work through the math part of this, confirm it common sense wise, but make sure you can work through the math part of it, because we're going to get to problems that you can't shortcut, and you're going to be able to need to work through this. I'm going to call it a formula. I'm using air quotes. I know you can't see that, but it's a formula, yes, but it's a very basic idea that, hey, when I see this or, I'm just going to go straight to add. All right.